Hello and welcome to this PV Tech Talk product series webinar in partnership with SENTECH Instruments. This 30-minute webinar is designed to introduce you to the SENPERC PV tool, its key features and benefits and applications for solar cell film thickness measurements. This is Mark Osborne, Senior News Editor at PV Tech and your regular moderator for PV Tech's Tech Talk series of webinars. We plan to begin with a brief introduction from Friedrich Wittig, Senior Manager at SENTECH, but will also be announced as the company's forthcoming CEO and shareholder in charge of driving and executing the direction of SENTECH's strategy and business development going forward. This will be followed by a technical presentation by Sven Peters, an application engineer for spectroscopic ellipsometry and reflectometry at SENTECH for around 20 years. As normal, we will have staff from SENTECH on the call to answer any questions during the presentation, and we aim to have around 10 minutes at the end for a short Q&A. Okay, well, that's it for me at this time, and I will pass this over to Friedrich. Welcome, Friedrich. The floor is yours.
Thank you so much, Mark, and thanks especially for the kind introduction. Yeah, you are right now seeing the first slide of our presentation. Thanks so much and a warm welcome from Berlin. And today we present on the SENPERC PV, one of the metrology tools for solar cell quality control. I would like to introduce SENTECH, a family-run business founded in 1990, so about 30 years old. And we are operating on two business fields, thin film metrology and plasma process technology. Today, thin film metrology is the big topic and especially quality control for PV. Our strengths are the non-invasive optical method. So therefore, after the quality control, you can still use the cells which have been checked. And you are supported with a worldwide web of service as well as application supporters. In these application labs, we can run demo samples so that the quality of your product is ensured when tested. This is also given by the 20 years of experience that our engineers have in PV quality control. This gave us the good position in the global PV market of more than 500 tools placed in the market. Right now, I'm very proud to show you the first slide once again, which is the SENTECH building. Right now we extended it, the size has been doubled, and with the 100 employees and growing, I would like to proudly give over to the expert for PV market, Sven Peters. Stage is yours, Sven. And as we go with Corona, here comes Sven.
Hello, everybody. I'm Sven Peters. Thank you for the kind introduction to Mark and to Friedrich. Yes, I would like to introduce the SENPERC PV metrology tool to you. This is for thin film metrology in solar cell quality control. And we are facing, or the customers of us in the PV market are facing the challenge that in, for example, PERC solar cell production, there is a process-depending variation in film thicknesses and optical constants of the functional films in the PERC solar cells. And these variations, they depend strongly on the deposition line operation time, for example, as well as on the cell location on the carrier. Therefore, the manufacturers request a fast and non-invasive measurement method to assure a constant quality of their cells. Furthermore, they request an easy-to-operate tool, and what we can offer, our solution here, will be the SENPERC PV, which utilizes a contactless optical method for the accurate and very precise measurement of both the film thickness and the optical constants of these films. Because both determine the quality of the solar cell, which can mean in the end the solar cell has passed or needs to be rejected. The instrument offers a two-step operation, so meaning we are placing the cell on the device and then we simply push the measure button. After a couple of seconds then, the result of the cell quality will be shown to the operator. And additionally to that, the results are automatically stored into an SQL database. So what kind of applications in terms of PERC solar cells can be solved? Here we have the aluminum oxide layer on the rear side of the PERC solar cell. In terms of the double layer stack of silicon nitride and aluminum oxide, we can measure this on damaged edge silicon samples as well. And concerning the front side of PERC solar cells, there is a silicon nitride film, which of course can also be measured concerning the film thickness and refractive index. But there is more. The SENPERC PV can also measure other types of solar cells. To name the heterojunction technology cells based on amorphous silicon, or the TOPcon technology based on polysilicon samples, and also recently the upcoming perovskite tandem solar cells as well. Let's have a look at the instrument itself. So what we can see here, we see this big box. We call this a compact design because all the components we need are integrated in this box. So the optics, the computer, the controllers are all integrated in this one single box. So no other components are around this setup. Here at the top, we can see the sample platform. This one holds solar cells with dimensions up to 220 by 220 square millimeters. The measurement position will be here up in the center position. We can also see here the touch screen with the recipe-oriented user interface on top. At the top, the front left side here, we find the control panel for the operator. Having a closer look at the control panel, it consists of just a few buttons for switching the system on and off. But the most important one will be the start button, because this is the single button the operator has to use to initialize the measurement to get the results of the sample. If something went wrong, he can also cancel the current measurement by pressing this button. So let's have a look at the way how to place a sample on top of the SENPERC PV. On the left-hand side, we see the way how to place acidic textured or even polished cell surfaces. They have this kind of more or less isotropic rough surface, and they are placed horizontally on the slit here with the measurement position right in the center position. In terms of the alkaline textured solar cells, they exhibit pyramids on top. The sample is slid into this tilted position here to bring the faces of these pyramids into the horizontal position to be measured properly. In order to understand better why this is such an advantage, I will show the way how our conventional setup of measurement tools is operated. So here we see now the sample facing up. The optical heads are on top of the sample, and using the screws here on the stage in conjunction with this optical head here, we are able to align height and tilt of these samples properly. In case of the samples which have to be placed tilted, we even have to exchange the flat sample stage here by a tilted sample stage, making the operation even more complex. And this is why this kind of technique here with this holder featuring both possible samples in one instrument makes it so much easier to use, also eliminating the alignment of the samples anyway. So let me show you a short video how this operation actually is done. So here the video starts. So we see here the alkaline textured solar cells put into the slit in the slanted position. Now the measurement is running because the start button was pressed. Now a couple of seconds later, measurement is finished, results are shown, and the sample can be taken away. And here is the way how to place the acidic textured surfaces, simply laid flat. Also, measurement time only took just a few seconds, and the operator can leave the system immediately. So let's have a closer look at the SENPERC user interface. Here, right at the top, there is a drop-down menu for selecting the proper recipe for a specific solar cell application. Right below this is a way to select the cell which comes from a certain reactor. In the moment here, we can select up to 4 reactors, but this is, of course, adjustable to the customer needs. To the right side of this, we find the position selector, where we can say at which position the solar cell should be measured, in the center, in the edge, at the top, and so on. Below that part, we find the results section. And here, their sign here now indicates that the quality of the sample was okay and it's passed. At the bottom, we find the entries in the SQL database, which I will explain in more detail soon. So let's have a look at the position selection. So up to 9 positions can be measured for each single solar cell by selecting one of these positions. Also, here the graph will visualize how to place the solar cell on the stage in order to measure the positions properly. In terms of the alkaline textured solar cells, where we have to slide in the sample in the inclined position, of course, we can only measure the center position of these cells, so no manual mapping is possible here. The results section looks like this. Here in this example, we find the results for the film thickness of silicon nitride, as well as the refractive index of silicon nitride. Here we find the target values we want to achieve and the current values we have recently measured. The graph here shows how the current values will be in relation to the target values and to the specification limits for these kind of wafers for both thickness and refractive index. The SQL database here shows the same information for the recent results. So here the green lines show the limits according to the green range here in the results section on the left-hand side. When they are outside these green lines, we are out of specs, and these are the rejected wafers. The timeline here can be selected between minutes or even months and is completely user adjustable how long this period will be. So I have been talking about recipes. Recipes for different applications can be created as a service from SENTECH Instruments, but also new recipes can be created by the customer itself, or existing recipes can be adjusted to the customer needs. And this here screen here shows how this is done. The most important section here is defining target values, the lower and maximum limitations for each value for refractive index and thickness, when film thickness and refractive index are out of spec, and even further information like, for example, offset when, for example, a matching is necessary. These settings are then saved in a recipe where we see the name here at the top. As well, there is a description file on how to model and how to analyze these films. This technique I will explain soon how this will work. And this is the technology behind it. So this is what our optical measurement technique now is doing. So here we find having an optical measurement technique is leading or yielding to a pair of optical spectra, now here represented just by a single spectrum. And what we have to do now is we have to build an optical model in the computer software, describing our sample. So describing the substrate, which will most likely be silicon, describing the layer stack. In case of PERC front side, it will be silicon nitride. Of back side, it will be a double layer of nitride and oxide. And off top, there will be air. And we have to assume, we have to put in some starting values for the film thickness of these layers and the optical constants. What we do next is that we let this model run through the computer engine, calculating also optical spectra based on our optical model. And now these spectra will more or less look very similar to our measured spectra. This is shown here. So it's similar, but it's not perfectly the same because our assumption, our input is not exactly representing the sample. And now there's a fit procedure running where the computer is changing our assumed thickness and optical constants value in order to achieve a perfect match between the model and the measured curve, which is shown here. Once we achieve the status, we can say now that reading out the current thickness and optical constants from our optical model will perfectly represent the real values of thickness and N of our film in our stack. And here I have prepared a couple of examples. Starting with a PERC cell, we find here an application for the front side where we have a simple single silicon nitride film on crystalline silicon. So our model is now describing a silicon nitride on the silicon substrate with a thickness of 80 nanometers and a refractive index of 2.0. So now we are running through the computer engine and we find here the red curves are already pretty similar to the measured curves, but they are not fitting perfectly. So let the computer now run the fit procedure, and matching the model curve perfectly to the measured curve will lead to our output. So the results will be now that the film thickness of the film is not as assumed 80 nanometers, but only 65 nanometers, and the refractive index is 2.05 instead of 2.0. Having a look into the second example of a PERC cell on the rear side, where we have a double layer stack on a crystalline silicon, we put in the values for the aluminum oxide film of 30 nanometers, which will be the typical range from about 510 to 30 nanometers for aluminum oxide, covered by a silicon nitride of about 130 nanometers with a high refractive index of 2.2. Again, we run this through the computer engine and we find here the red curve modeled, already fitting quite well to the measured curves, but not perfectly. Then again, we apply the fitting procedure, acquiring a perfect match between the model and the measurement, so we can read out the results for our PERC solar cell, meaning that the silicon nitride film is now determined to be 180 nanometers with a refractive index of 2.22. So in terms of N, it's very similar, only the film thickness is quite different, while the aluminum oxide film thickness is very close to the assumed value. Now let's go into some other applications to the heterojunction solar cells, where we have completely different materials in our stack. So here we have an amorphous silicon on our crystalline silicon substrate covered by ITO film on top. The intended film thicknesses are 10 nanometers for the amorphous silicon. For ITO, it was 80 nanometers with a refractive index of 1.9. Again, you know this process already. We put this into the computer engine. We get the calculated spectra. Of course, we expect to have a slight of a mismatch between measured and modeled curves, but the fit procedure now removes this deviation again, obtaining a perfect fit, leading to the results for film thickness and refractive index for the ITO film. So the ITO film became much thicker than expected, while the amorphous silicon is well in the expected range with 9 nanometers in relation to 10 nanometers. And my last example will be the TOPcon technology, where a polysilicon film is deposited on its thin SiO2 film on crystalline silicon. This is intended to be a single film, but our measurement technique is so sensitive that we are able to find that during this deposition process, there seems to be some changes leading to not a single film on top, but to a double film layer structure. So we had to split the single film into a top and bottom film because we will have different optical constants here. Additionally, polysilicon is known to grow with a rough surface. That's why we also have to include a roughness on top of the polysilicon film. The SiO2 film thickness separating the substrate from the polysilicon is expected to be about 2 nanometers. Again, running through the computer program, here we find that our assumption, so the red model curves are already fitting the measured curves very well. Applying the fitting engine acquiring a perfect fit, now giving us the results. So the roughness is about 2 nanometers. The polysilicon film on top and the bottom silicon film thickness were determined. We can see that the refractive index difference is only 0.04. So it's quite little, but our measurement technique is so sensitive that even this little difference can be clearly seen in our modeling procedure. So the total thickness becomes 121 nanometers, so pretty close to the expected 130 nanometers. And the SiO2 film is determined to 1.8 nanometers, so very close to the expected 2 nanometers. So here we can see that we can also measure very, very complex multiple layer stacks with our technique, and that they can be analyzed successfully with a very high accuracy. So I will now conclude here. So we have seen today that our SENPERC PV is a very fast and very accurate quality control tool for solar cell applications. It has a solar cell self-alignment, a recipe-oriented user interface, and the push-button operation, making it very easy to use for operators. It features an integrated SQL database, and we have seen it's also capable for other various solar cell applications because of its modeling technique behind the measurement technique. So that's make it so future-proof also for emerging cell designs. So this was my talk. Thank you very much. And I will give back to Mark for the Q&A section. Thank you.
Well, thank you, Sven, and thank you, Friedrich. Just looking through some various questions here, but one I particularly like, and hopefully this is an easy one for you to kick off with, Sven. Obviously, the tool is called the SENPERC, but you've covered in great detail and really interesting information about alternative cell architectures. So what's behind the name there?
Oh, the name, yeah. So we came up with this name when we had the first questions to measure the rear side of the PERC solar cells. This is quite a few years ago. And then we had the requests for an easy measurement tool, and we were designing this tool. And yeah, those times the PERC application was the main application we had, and that's why we created this name for the tool. Even though nowadays we have other applications, but we stay with this name so far.
Okay. There's several questions here, and I'm going to sort of put a few together. But a key thing here being asked is from a validation, qualifying, I guess, or validating the SENPERC tool in either a lab or a production line. Can you sort of give your recommendations on that? People are just asking.
Oh yeah, we get these questions all the time because the customers need kind of a reference to test in order to qualify the system, because they have an ISO certification, for example. And what we offer are test samples. We have a couple of them, and they are certified here in our laboratory. And we have reference wafers, which are from the PTB, which is the Standardization Institute, which is comparable to the NIST in the United States. And so our reference wafers are then traceable to these PTB standards. So the customer has a very reliable reference tool in his hands to check the accuracy of his SENPERC galopsometer system.
Got it. Again, related to this is several questions here, but I guess this is actually, although it's offline, this is a fab tool. It's not just a laboratory tool.
Yeah, this is designed for the fab line, so you can place it directly next to your deposition chamber. So there is no need to put this tool into maybe the designed measurement sections of a fab line. So you have a short way from your deposition tool to your measurement tool. So there's no need to walk hundreds of meters to do a measurement. That makes it even quicker to get the results.
Okay, and I guess related here is actual sampling frequency time. What is recommended? Is there differences between, say, a PERC cell to a TOPcon cell?
Yeah. So what we see here in these cells is that the deposition chambers, they run pretty stable over a long period of time. But what you see is maybe the cycle time of the cleaning process of these systems is a couple of weeks, maybe 4 to 6 weeks. And during these 4 to 6 weeks, you can see a drift in the film thickness, in the optical constants of these instruments. So there is no need to measure every sample, but maybe every 50 minutes or every hour, there should be some samples measured, maybe from the center of the tray, or maybe from the edges, to also observe the homogeneity of the film thickness. Right.
Actually, this is it's a good point you mentioned there, because there's a question here. When the optical constant at the bottom layer is lower compared to the top layer, is the tool able to measure basically the thickness of the RI accuracy?
Yeah, this was the TOPcon example.
Yeah.
And yeah, this was also something we didn't expect, because originally you want to deposit a single film and you're expecting not such a result. But what you actually got here was 2 different films. So in the moment, I don't know if this example is really because of changes in the process, or sometimes people also have different deposition or different sputter sources. So that also can happen when you have 2 sources, one after the other, then you have also 2 different optical constants. But I have selected this example to show how sensitive our measurement method is, to that it can also see these tiny differences in the optical constants between these 2 polysilicon films here.
Right. Okay. Another recurring theme here, and I guess it's related to what I was saying about the sample frequency. Can the measured solar cells actually be put back into the processing steps again? It's not as in it's not damaged in any way.
Yeah, there's no damage. So you just place a sample on the stage, and you don't have to break the sample, so you can feed it back into your process. And if you keep the surface clean, then there's also no relevant contamination. So from our point of view, you can still use these samples to put them back into the process, so it can end up in a panel in the end.
Okay. Well, looking at the time, maybe just a few quick questions that I can fire at you. So obviously, the system uses a xenon lamp system. What's the kind of lifetime expectancy of this? And is there other sort of major consumables associated with the SENPERC tool?
Yeah, so the lamp itself is the main consumable here. There is an official lifetime for these lamps, which is about 2,000 hours. But from the praxis, we know that you can also use it even much longer. So there's no need to really replace it after 2,000 hours. We're looking for other things like the stability of the lamp. When this is dropping, then we have to replace it. Right,
got it. Okay, just a final one, I guess. Can the tool measure the reflectivity as well?
The reflectivity, in principle, yes. So the main goal here is to measure these two spectra we have seen, psi and delta, but the reflectivity is also possible to measure. Then this is just a question of how to tweak the software in order to do this. But in principle, yes.
Okay. Let me just squeeze in one more. We're only just slightly over, and there's some good questions here. I guess summing up with a couple of other points here, really about the from a recipe perspective and an analysis initially, you're recommending that these are done by yourselves first, and then followed up and qualified, your end. Why is that?
So we want to sell a system which really can solve the application of the customer, and that is why we request sending samples into our labs, where we can measure them by ourselves, building the optical models, checking the accuracy of our results, and then we can deliver in the end a system with the already prepared recipes where we know that they are going to work well. Got it.
Okay. Well, looking again, I think we've got through quite a few of the questions, and just to let people know, although the webinar actually is ending now, the platform will remain open for a little bit. So if you have any more questions, then SENTECH staff are here to help you. But once again, thank you so much, everybody. Thank you, Sven.
Yeah.
Thank you, Friedrich, for coming along today. And I hope this has proved very interesting. And it's one of my favorite topics. And it's nice to actually have an upstream technical issue to cover once in a while. So thanks again, everybody, for joining today. That's the end of this webinar. Thank you. Bye-bye.
Thank you. Bye-bye.